This video is the first in our series talking about nomenclature. We're going to start off this unit talking about ionic nomenclature, and in this video specifically simple ionic nomenclature or simple ionic compounds. We'll be working with ionic compounds for 2 days, and then we'll move over to covalent compounds, and then finally to acidic compounds. But for this first video, we want to talk about this specific objective, and that is the student will be able to identify, provide chemical formulae, and chemical names for simple ionic compounds. Now, a word that I'm going to be using often in this video are binary compounds. Binary essentially just means that there are two different elements in that compound. So in chemical nomenclature, it's going to be really important for us to figure out what type of compound we're dealing with. And the main reason for that, and that's sort of identified here on this slide here, it says, what is the importance of identifying an element's metallic character or lack thereof? And the really important part about this is that different compounds, so whether they be metallic or ionic or covalent, or if they're an acidic compound, they essentially have their own set of rules that we use to name those substances. Now, here are the 4 different types of compounds. There could be a metallic compound, so that's when a metal binds with another metal. It can be an ionic compound, when a metal binds with a nonmetal. A covalent compound is when 2 nonmetals will come together and be covalently bound. And then finally, an acidic compound is sort of this almost transition between ionic and covalent. It's really 2 nonmetals together. That first nonmetal is going to be a hydrogen, and that second nonmetal can be any other random nonmetal. What we're going to find out whenever we talk when we talk about acid nomenclature is that acids kind of are a linkage between ionic nomenclature and covalent compounds, but that really isn't the focus here of this video. It really is the ionic compound. So the importance of this is that once I define what type of compound I'm talking about, then I'm going to apply certain rules and procedures to naming that compound. So let's give a background about what ionic compounds are. So as you'll notice here, it says ionic compounds are composed of a metal cation bound to a non-metal anion. Remember that cations are positively charged, whereas anions are negatively charged. All right, so that's a really important distinction to make, because this is an ionic compound, so it has to be composed of ions in order for it to be called an ionic compound. In ionic compounds, electrons are transferred between the atoms. So you'll notice that these red electrons located here on these atoms in this graphic, eventually what is going to happen is an electron is transferred. This is a valence electron. An electron is then transferred over to another atom. So then that really poses an important question. Why is the electron transfer process important? And the reason for this is that oxidation numbers are going to be swapped in ionic compounds. Now, for right now, this probably seems like I'm talking in abstractions, but I promise you, once we take a look at some of the examples, you'll be able to make this concept of oxidation number swapping, we'll be able to make that a little bit more concrete. But for right now, you need to understand that ionic compounds are a metal bound to a nonmetal, that the electrons are transferred in ionic compounds, and that the oxidation numbers are also going to be swapped whenever I write or name the compound. So we can remember our discussion about oxidation numbers. The one point that I want to make before we talk about the trends here is that oxidation numbers is a word that I'm going to use many other words to describe. And what I mean by that is that I can say any one of these words here. So oxidation number can also refer to oxidation state, valence number, valency, ionic charge. Any of those words I can use to talk about the oxidation number. For the most part, in my conversation, I'm going to try to use the word ionic charge to kind of impress upon you that these are ionic substances. Each of the atoms in that ionic compound has an ionic charge. But just know I have a really bad habit of interchanging all of these words, because they are interchangeable. So you can remember from the previous unit that oxidation numbers have a certain trend on the periodic table. For example, I know that this group all has +1 oxidation numbers. This group here, the nitrogen group, all has -3 oxidation numbers, and so on and so forth. The transition metals are wacky and weird and crazy like they always are, and they have a variable oxidation number. For right now, in this video, we're not going to focus on those. We're going to focus on our main group elements. So those are the elements in the S and P blocks. And then in another video, we'll discuss what happens when we have our wacky, crazy family that is the transition metals. But for right now, we're going to focus on the ionic charges of the main group elements and what happens when I have a metal from the S block bound to a nonmetal from the P block. And again, this is what we call binary compounds. Let's take a look at some of the examples and get some of those abstractions I've been talking about in the rules and make them a little bit more concrete in these examples. Now, I will also tell you that these examples that I'm about to show you are also in your handout. Please follow along with those examples in the handout so you don't have to worry about writing down too much. Also in the notes, you'll notice that all of the steps are written out for you. Please take a look at those steps as well and really kind of memorize the steps instead of just trying to memorize names or memorize formulas. So I'm going to start over here on the right side of your screen where we talk about naming the compound. For the most part, naming the compound is quite simple. All I have to do is recognize what two elements there are in the compound. So the first element is going to be strontium, and the second element is nitrogen. Once I've identified the elements in the compound, there really is only one change that I need to make when we're talking about binary compounds, and that always comes to the nonmetal in the compound. So our nonmetal in this compound is going to be nitrogen, and I'll show you the change that we're going to make. The name of this compound is going to be strontium nitride. That's the following name. So notice what happens, what change I make to the nonmetal stem. I basically drop the second syllable here and add in a new syllable that is IDE. I'm going to do that for every single nonmetal stem that I find in an ionic compound. So the full name is going to be strontium, that's the first element in the compound, and then nitrogen, but remember to change that now so the full name becomes strontium nitride. The final point that I want to talk about in naming a compound is that although what I'm about to show you isn't important for this compound, it is going to be important in the future. So I want us to go ahead and get this concept under our belt so that we feel comfortable later on when it really becomes important. I want us to go ahead and start checking the oxidation numbers of these substances. And what we're going to do by this is we're going to swap the oxidation numbers like I mentioned in a previous slide. And by swapping the oxidation numbers, I really mean take a look at these subscript numbers. That nitrogen, the 2 there on the nitrogen, originally came from the strontium compound. And that's important because if we take a look at the periodic table, the strontium should have a +2 charge. So notice that I just swapped that oxidation number, the 2 that was a subscript next to the nitrogen, now becomes the oxidation number of the strontium. If you take a look at your periodic table right now, you'll notice that strontium is in group 2 or 2A. It should have a +2 oxidation number. The same thing can be said about the nitrogen. If I take this 3 down here next to the nitrogen, it's going to form a -3 charge. And if you look at nitrogen on the periodic table, it in fact has a -3 oxidation number. That's where these numbers come from. So again, like I said, it's not too important here for this problem, but it is going to be important in the future. Now, a question you may be asking yourself right now, and it's a very legitimate question, is how do I know that the strontium has a positive charge? And how do I know that the nitrogen has a negative charge without looking at the periodic table? And we're going to establish a rule right now that's really important, and that's this rule. The cation plus anion rule. And basically what that says is the cation is going to come first in the ionic substance. The anion is going to come second in the ionic substance. Cations are always positively charged. Anions are always negatively charged. So my positive charge is always going to be first. My negative charge is always going to be second. Let's now take a look at the left side of the screen here where I'm going to write the formula. So I'm given this example of calcium chloride. The very first thing that I'm going to do is I'm going to figure out what my chemical symbols are for these elements. So I know that calcium is Ca, and I know that chlorine is Cl. Remember, this IDE ending is a suffix that I always attach to my nonmetal. So chloride has to come from the element chlorine. So it's that same change that we made in the nitrogen in the previous problem. The second step that I'm going to do is I'm going to assign the oxidation numbers to these substances by looking at the periodic table. So I know by looking on the periodic table, calcium is a positive 2 ion, and the chlorine is a negative 1 oxidation number. Now, in my third step, what I'm going to do is I'm going to crisscross those oxidation numbers, or swap the oxidation numbers. So the calcium has the positive 2 charge, the chlorine has a negative 1 charge. When these guys swap, they're going to become my subscripts. Notice that when they do cross down, I lose the positive and negative charge. I'm never going to have positive and negative charges in chemistry as a subscript. That's just never going to happen here. Okay? So I have Ca1, Cl2. But just like in math, there's no need to write ones because they're understood. You would never write something in your algebra class. You would never write 1x. You would just write it as x because the 1 is redundant. And that same math applies here in chemistry. So my final answer is CaCl2. So that's my final answer. I'm going to follow these same steps every single time. Okay, let's take a look at our next set of examples. So I'm going to start here on the left side of the screen with writing the formula. I need to write the formula for sodium bromide. So again, as always, I'm going to identify the chemical symbols. So sodium is Na, and bromide, remember the IDE ending, is changed for the nonmetal. So bromide has to come from bromine. The symbol for bromine is Br. Now let's take a look at our oxidation numbers. Sodium has a positive 1, bromine has a negative 1. So whenever these oxidation numbers cross down, as I always do in my swap, it becomes Na1, Br1. But again, remember, we don't write understood ones here. So my answer becomes NaBr. That is the formula for sodium bromide. Let's take a look at this next example in naming the compound. So I'm given the chemical formula MgO. I know that this is a binary compound because it only consists of 2 different elements, magnesium and oxygen. Let's work this problem in the exact reverse order that we worked the last problem in. So in the other sodium bromide example, we dealt with the oxidation numbers and they're reducing at the last moment. Let's do this in reverse. So if I take a look at the subscripts here, it looks like there's an understood 1 here next to the magnesium and an understood magnesium or an understood 1 next to the oxygen. If I reverse swap these oxidation numbers, it looks like the magnesium has a positive 1 charge and the oxygen has a negative 1 charge. This is a moment where a big red flag pops up. Because if you take a look at your periodic table, there is no circumstance where a magnesium ion or whether a magnesium atom exhibits a positive 1 charge. That just doesn't exist here in our world. So what must have happened? The answer to that question is that these two oxidation numbers must have been the same. Okay? Because magnesium, in fact, in our real world, has a positive 2 charge. That's the real oxidation number of magnesium, positive 2. And in that case, that means that if this reduced down from a positive 2 to a positive 1 before I crisscrossed my oxidation numbers, then in fact the real oxidation number for the oxygen is a negative 2. And that's consistent with the data that we have on the periodic table. We know that oxygen is in group 16 and has to have a negative 2 charge. So what happens in this case, if I have a positive 2 ion that meets up with a negative 2 ion, whenever they swap their oxidation numbers, they're actually going to be reduced down because they can be divided by the same number. That's really important, okay? The same thing happens if I have a positive 1 charge with a negative 1 charge, like we saw in the sodium bromide. These guys, one, canceled each other out, but they also reduce down because they are ones, and we don't write understood ones. But the same thing can be said if a positive 3 charge meets up with a negative 3 charge. These guys can reduce down to ones, because they can both be divided by 3. And then, of course, we don't write ones because they're understood, so I'm not going to write them at all. That is only a case when ions have the same charge. I'm going to modify that in a little bit by saying, essentially, I'm going to reduce terms down. So if a positive 2 charge meets up with a negative 4 charge, well, those two numbers can be divisible by 2. I'm going to show you an example of that later on. But for right now, let's go ahead and name this compound. So right now, it's not really important to know the oxidation of the metal, but pretty soon, in the next video, it's going to be really important. So we're going to kind of get practice on that. So, as always, we name the metal. So magnesium. And then this non-metal is oxygen, but remember you're going to drop the second vowel in oxygen, so that's going to be gen part, and you're going to add the IDE ending. So magnesium oxide, and that's the name of this substance. Let's now go ahead and take a look at our last set of examples then. So writing the formula, we're going to start off with barium selenide. Let's go ahead and write those oxidation numbers. So it looks like barium has a positive 2 charge based on what's going on in our periodic table. And selenium, which comes from selenide, has a negative 2 charge. So again, we're kind of seeing what we saw in the previous example. So again, I go ahead and write my chemical symbols. So barium is Ba, and it has a positive 2 charge. Selenium is Se, and it has a 2 minus charge. Let's go ahead and cross the oxidation numbers. But what is really most important here, once I've crossed my oxidation numbers down to subscripts, you have to ask yourself, can these numbers be reduced any further? And of course, both of these number 2's can be divided by 2 to give us a 1. So in fact, what's going to happen is my chemical symbol, or the formula, is just going to be BASE. Notice it's the exact same example in reverse of what we talked about before. Magnesium oxide is just MgO, just like barium selenide is going to be BASE. For this last example, we have K3P. K is the symbol for potassium, and P is the symbol for phosphorus. So the name of this compound is going to be potassium phosphide. And also to drive that point home, I want to reverse crisscross the oxidation numbers so we can see that the potassium has a positive 1 and that this 3 originated from the phosphorus, which has a negative 3 charge. So notice that these oxidation numbers, these subscripts for ionic compounds, they come from the oxidation numbers of the metals or the nonmetal in the compound.